Okay, today we are going to start on module 3, which is pavement design and construction. First of all, what do we mean with pavement? What is the definition of pavement? In terms of highway design, it means the total thickness of road, including surfacing, base, and some base of any. That means pavement includes all structural layers of road structure laying on subgrade on the road. Okay, what's the functionality of pavement? Okay, so that means when we say this definition, so that's the natural ground. Okay, whatever comes on top here for the cars to drive to go through on, this is pavement. Functionality. What is the functionality of pavement? Pavement, the functionality of pavement is basically to distribute traffic wheel loads to the natural ground. Okay, so that means that's the natural ground here. Okay, that's natural soil. If the wheels of trucks go on this, it will gonna go down. The bearing capacity for this is too low. It cannot take the wheel loads. So we make this structure, which we call pavement, so the wheel load spread over an area with little, the load is distributed such that the pressure here is less than the bearing capacity of the soil. Clear? So that's the functionality. So the functionality of the pavement is to distribute the traffic wheel loads to the natural ground. Okay? Then, what are the design parameters for the pavement? First of all, it's the traffic loading, the loads. Second, the property of the natural soil, the subgrade, okay, or the bearing capacity primarily. Then the type of pavement and the construction material, whether we have a rigid pavement or flexible pavement. Both they are different in design and everything. So regarding the traffic loading, okay, that depends on the type of traffic flow that goes in. For example, if we are designing a highway that is connecting a port or a seaport or something, this highway is basically going to be, it will have high percentage of heavy vehicles and trucks. Okay, so the axial load, the frequency of heavy axial loads on that road will be higher. So this will need stronger design. But if we are designing a suburban area with minimum heavy vehicles, the design will be different. Also the subgrade. If we have a good sandy oil, a good sandy subgrade soil, okay, it's better than having a clay soil. The bearing capacity is different, okay? And the pavement type basically dictates the design method. So first of all, we start with the load configuration for highways. We have variety of vehicles driving on the highway. So we have passenger cars, we have trucks, we have trailers. So this combination of different axial loads, we converted into what we call equivalent single axial load. And based on this, how many equivalent single axial load is going over the pavement, that's what we will use as a design load. The equivalent single axial load is 18,000 pounds or 80 kilonewtons. Okay. The load configuration, that's another important issue, specifically for runways. Okay, because as we can see in runways, that's not a typical, it's not like a highway. No, Here we don't use the equivalent single axle load. The design criteria is totally different. It's according to the Federal Aviation Administration regulations, AC 150/53020-6E. This basically stipulate for different aircraft types, the design loads, the impact load, and all of these, impact factor, and all of these criteria. Because here we have a totally different story. We have, the single wheel might have maybe 30 tons on it. Okay. Okay, again, the load configuration, as we mentioned for runways specifically, the configuration of the tires, it's important. As you can see, here we don't have an overlap between the load. Okay, here we have overlap after the distribution, so the stress here will be higher. Okay, if that's the stress here distributed on the subgrade, but the overlap causes doubling the stress on the surface. So that this is a critical issue that we must take into consideration. Then we move to the subgrade, which is basically the subgrade natural soil properties. Basically, subgrade, that's the foundation of the road. That's where we are building the road. It's important for structure and pavement life. Okay, first of all, it should not deflect excessively due to dynamic loading. Okay, it may be infill or embankment, so we have to be careful about that. How can we characterize the subgrade? Basically, we have the California bearing ratio. Okay, it measures basically the shearing strength, the shearing resistance, and its units, it's in percent. And we have the resilient modulus. There's MR and CBR. Those are the primary criteria that we use in designing a pavement. These are the primary criteria for the subgrade properties. Okay. Now, for the pavement types, we have two types. We have flexible pavement, okay, which is basically asphalt pavement, and we have rigid pavement, which is basically concrete pavement. As we can see, the structure is kind of similar. We have the natural formation, that's the natural soil, and we have here what we call the base layer, okay, the sub base, I'm sorry, and this is the first asphalt layer, and this is the surface layer. In concrete, we have only the sub base layer and the concrete layer. The concrete layer, it's either reinforced or just plain concrete. What you see in this sketch is basically these are not reinforcement. These are connecting dowels, and we will, explain it later. Any questions so far? That's again a slice into rigid pavement and flexible pavement. As we can see, this is the natural ground. This is the sub base, which is basically crushed stones and stuff like that. Then we have here a concrete layer. Here we have base layer, and we have the surface course and the surface dressing. Okay, how pavement type affects the design? First of all, as you can see, the flexible pavement, the load is more concentrated, and that's the distribution of the load in the longitudinal direction. For rigid pavement, the concrete is basically a slab supported by, so when it distributes the load, it distributes the load on a larger area, as we can see here. So that's one of the major differences. That's why we use these rigid pavement for runways. However, if you can see, especially for the impact of the aircrafts when it's making touchdown on the runway, in the taxiways, you can see that in some cases they use flexible pavement for taxiways. Okay. Okay, this is a comparison between the flexible pavement and rigid pavement. the design principle for flexible pavement, the asphalt pavement, is basically empirical method based on load distribution characteristics and the characteristics of the components. The rigid pavement, it's basically structural design. It's designed and analyzed using the elastic theory, as if you are designing a beam or a slab. For the material, flexible pavement, we use granular material, okay? But here we use concrete, cement concrete, either plain or reinforced. And sometimes it's pre-stressed, by the way. For construction, it's constructed into a number of layers. Here, it's laid in slabs, okay? The stress in flexible pavement transmits vertically, okay, and compressive stresses due to the lower layers. But here it generates a tensile stress, okay, and temperature increases. For normal loading, it's elastic deformation. For rigid pavement, it acts as a beam or cantilever. For excessive loading, it causes depression. But for concrete pavement, it causes cracks and permanent damage. Both are permanent damage, by the way. Okay? For temperature, for flexible pavement, there is no stress produced. But for rigid pavement, there is a stress, thermal stress, that is generated. Okay, regarding opening to traffic, for flexible pavement, we can open the road to traffic within 24 hours of compacting constructing the surface layer. But for rigid pavement, we need to leave it at least 14 days for concrete to cure. So these are the fundamental differences between, or this is a comparison between rigid and flexible pavement. This is basically are the main elements of rigid pavement. As we can see here, it's divided into slabs, okay? And there is longitudinal joints between the slabs, and there is transversal joints, okay? We have tie bars connecting the longitudinal slabs, okay? This is the subgrade, and this is the subbase, okay? And there's dowel bars connecting the slabs here, and we have surface smoothness. That's the finishing of the rigid pavement or the concrete. This is also again elements of rigid pavement. As you can see, it's divided into slabs almost 10 meters, okay, and width of each slab, between 4.5 to 5.5 meters, in that neighborhood, okay. Okay, now for rigid pavements, we have a group of joints. So we start with the contraction joints. The contraction joints are joints that or weakened planes in the concrete. Its purpose is basically to relieve tensile stresses in the concrete due to change in moisture content, which is basically drying shrinkage, and or temperature. Okay, the purpose of these contraction joints is to prevent formation of irregular cracks due to restraint. For example, if we don't do that, if we say this is the top surface of the, okay, if we have this large surface of concrete and without the contraction cracks, we will have cracks like this, randomly generated, when the concrete starts curing and drying, okay, or maybe due to temperature changes. But with the contraction joints, what we do, that's a top view, we make these contraction joints like this. If we take a section here, that's what you'll see. After pouring the concrete here, or after laying the concrete here, we cut a groove deep, and this groove is filled with rubber material or bituminous or something like that to seal it. Okay, so when the concrete starts shrinking, okay, it creates a crack here, or when the concrete starts drying. So these are the contraction cracks. If there's thermal change or something, that's, you know, it takes care of that. Longitudinal joints. Again, the longitudinal joints, okay, are joined, lanes are jointed together by joining joint known as longitudinal joints. Okay, usually these are the longitudinal joints, and usually we place it at the lanes. This, you know, if we have here one lane, we make a longitudinal joint in this segment or this part. These joints are provided in multi-lane pavement, and if the pavement width is more than 4.5 meters, okay, they are provided normally at 3.5 meters center to center, which is almost that's the lane width. The purpose of this longitudinal joints is to relieve stress due to warping. Okay, warping is basically, if you have a surface like this, the soil underneath it is not equal. It's not equal in strength. So there is a potential that one will rotate different than the other. So this is what we mean with warping. Okay, to allow differential shrinkage, swelling, okay, due to changes in subgrade moisture, to prevent longitudinal cracks. So that's also similar to the contraction joints, but we make it longitudinal. The procedure of construction initially joint in cut to a depth of 1/3 the slab thickness. Okay, initially joints is cut to a depth of 1/3 slab thickness plus or minus 5 millimeter. The tie bars are provided at the joints, not for load transfer but for keeping the adjoining slabs together. Okay, basically we put dowels to maintain the slabs, the shear strength or the connection between the two joints. Expansion joints. This is for temperature. Okay, so we have these expansion joints. The expansion joints are different because we stop here and we put a dowel. Okay, then when we start, you know, the second slab, we put this filler, which is basically a rubber material. Then we put this jacket cylinder, okay, with a material inside it, like, you know, oily material inside. Then we put the, you know, we lay the concrete for the other slab. So this way, we allow for expansion, that these can expand, and there is the rubber elastic material in between, and the spacing between them is basically 20 millimeter width. That's the distance, and there's no bonding, so this dowel can go in and out in millimeters actually, but the shear is maintained. It transfers shears, but it does not transfer axial forces. Okay, you know, but again, this expansion joints are full depth. It's not you know, part of the slab. The construction joint. Of course, we cannot build, you know, the entire segment in one day. We cannot, you know, pour the concrete. So we have what we call construction joints. That's the joints that we stop working for the day and we start in the next day. So it's basically something like that. We keep a dowel here, then we put you know, wood restrainer here. Then after that, we finish it by clearing this groove, which is maybe 20 to 25 millimeter deep, and it's 10 to 12 millimeters width. Then we fill it later on with bituminous material just to seal it. Okay, and here there is a full bond and there is a full bond between the there is no jacketing or something like the expansion joints. These are examples for the tie bars on the longitudinal, and this is the dowels on the the other joints. This is an reinforced slab, okay, and you can see the longitudinal dowel, the longitudinal joints, and this is the dowels here. You see these dowels. This is again, this is a transversal joint, okay, and this is a rubber material, and they are gonna bore the concrete in this segment. Any questions so far? Okay, what are the steps for rigid pavement construction? First of all, we start with the subgrade leveling. That's the first task, is leveling the subgrade, the natural soil. Okay, we try to level it, okay, to go with the vertical alignment and the horizontal alignment. Then we make a compaction after the leveling to make sure that it's well compacted. Then we put laying the sub base layer, which is basically an aggregate, okay, and it helps in distributing the load on the subgrade. So we start laying this sub base, then we start compacting the sub base, as we can see here, and these are the levels. As you can see, these are placed on the side of the road, so the compaction should be following or respecting these elevations. Okay, if you are designing, if you have a vertical alignment, that's where we place the vertical alignment. If you are designing a super elevation, that's where these are going to be represented, your design. Then after that, okay, we lay the dowels, okay, and these are the tie bars, and these the dowels longitudinal, and this is the machine that usually we use in laying the concrete on the on the road. Then this is another machine that is laying and finishing at the same times, and sometimes we use this machine for finishing the rigid pavement, the concrete. Then for runways, we use this machine, which is basically a grooving machine. This machine has a bunch of wheel saws like this, okay, and it goes transversely into the runway to make these grooves. These grooves, so if you take a section here, this is what you will see. The purpose of these grooves is basically to make sure that in case of raining, there is no formation for water on the runway. So it's basically to make sure that all the water that due to rain or something is not going to stay here, and it will not develop a hydrofilm. If it develops hydrofilm, that will affect aircrafts in stopping, and actually they started doing this after a very famous accident that I think happened maybe in the 80s or something like that. Okay, any question now regarding rigid pavement? Okay, now we go to flexible pavement construction methods. It's quite similar. Okay, so we start again with subgrade leveling, then compaction of subgrades, then laying the subbase, then compacting the subbase. Okay, that's basically the same for both. But from here, things starts to be different. First, before we start to have a prime coat. This prime coat is a tacky material, bituminous, okay, and its purpose is basically to seal the sub base and the natural ground, the natural soil, from water and from leaking water, because if water leaks under the pavement, it's going to cause damage. In case of rigid pavement, the concrete itself is a good sealer. Okay, then we place laying the base course. This is the pavement. If you are driving on a highway during construction, sometimes you see this rough pavement. Okay, so that's the base course. Okay, it's laid by this machine. This machine is called finisher. The asphalt mix come and from the batch plant, and they put it here, and it start going with there's laser leveling for this part, so the technician can control the thickness and the slope and a lot of things he can control in this, and even the super elevation, the inclination. Okay, so as you can see, we have here one finisher and a second finisher. They are both working at the same time. So this way we don't have this visible construction joints in the pavement surface. Okay, and both are followed with compactors. So here we have the surface layer. Okay, that's the smooth layer that we all so, and this is the compaction for it. Okay, then after that we go to the pavement marking and signage. Okay, that's the final step in pavement in flexible pavement construction. Any questions so far? Okay, now we have some key aspects in pavement construction, specifically for site engineers, that they need to pay attention to. First of all, these are the geometric layout. You have to pay attention to cut, fill, and super elevation. That's surveying part. You need to be able to identify the quantities of cut and fill, because this means a lot of money. And the super elevation, that means safety in the construction and the design itself, that you are doing the design correctly. Then we have the subgrade soil. The subgrade soil, it's important that you make sure that the soil classification is according to the design. So you have to keep an eye on the quality of the soil during the natural or the subgrade leveling. Okay, and there is the bearing capacity of subgrade soil, okay, through the CBR, and there is the subgrade compaction quality control. This is very important test that during construction of pavement, regardless it's rigid or flexible, the sand cone test to measure that the compaction is sufficient and the layer reached the density that we need. Basically, this step, okay, for compacting the layers of the crushed stone here, for example, this is very important. Why? Because when the sub base is laid, okay, it's disturbed soil and its density is low, right? So that's why we compact it, to increase its density. Once the density increased, its ability to carry load increases significantly. And that's what we are looking for. We are looking for specific load bearing for this layer. This specific load bearing cannot be achieved if it's not compacted well. How can we know it's compacted well? By measuring its density, by the sand cone test. Okay, so this is, if you are going to be a site engineer for highway construction, that's a very crucial test for compaction. And there is another method used for, instead of the sand cone test, this is the, we'll discuss it later. So the cut and fill segments, you should be able to calculate the volumes for cut and fill, clearly. And you can see here we have a fill section, we have a cut section. Okay, the fill section, this is one of the most challenging parts in highway construction. Why? Because you have to make this fill into layers. Each layer almost 25 centimeters. So if you have a filling for 1 meter, that means you have to do it into 4 to 3 phases. And in each phase, you have to make QC, quality control, for compaction. Otherwise, after the road is constructed and open to traffic, it will have what we call settlement. It will go down, and it will go down in a random way. So you will see the road wavy like this. Okay. For the cut section, you are just digging the area. It's not, as troublesome like this. But for the cut and fill section, sometimes you have the soil, level, the natural level is inclined. So you have to make cut from here and fill here. So that's also challenging, because you need to be able to retain this soil so it doesn't go this way. For lane widening, for example, okay, we do fill widening. Fill widening, basically, if that's the standard subgrade, we do fill widening to prevent this area from running this way. Any questions so far? Okay. Desired properties in subgrade soil, basically stability, that's one of the desired properties. Incompressibility, okay, so if it's compressible, that means with heavy loads, there will be settlement and random settlement. Permanency of strength, the strength is permanent, it's not changing with time. Minimum changes in volume and stability under adverse conditions of weather and groundwater. For example, if we have a swelling clay, okay, this is this is not desired at all in highway construction. Good drainage, for example, sand is perfect. It does not retain water in it. Ease of compaction, like sand, for example, and gravel, it's easy to compact. But for example, clay, it's difficult in compaction. Okay. Subgrade soil performance, we have the load bearing capacity and the moisture content and the shrinkage or swelling. These are key aspects that, so the load bearing capacity affected by the degree of compaction, as I mentioned, and moisture content and soil type. So that's the load bearing capacity is function of the degree of compaction, moisture content, and soil type. The moisture content, it affects the subgrade properties like load bearing capacity and shrinkage influenced by drainage. The moisture content, again, the ability of the soil type to get rid of water, okay, and also the groundwater table elevation, it affects the moisture content. Shrinkage or swelling, shrinkage, swelling, and frost heaving will tend to deform and crack any pavement type constructed over them. as again, if we have shrinking soil or swelling soil, both with snow and frosting, it will cause, you know, swelling, and it will just simply damage your pavement, regardless it's a rigid pavement or flexible pavement. The subgrade soil classification by AASHTO is basically, I think you have taken this this classification, correct? The unified soil classification.
Yes, we take it.
Okay, so we have, it's based on grain size, and it has 7 groups from A1 to A7. Unified soil classification. The most popular is G, gravel, W, well, clay, M, okay. So the group index GI is calculated through here, F minus 35 multiplied 0.2 plus 0.005 times the liquid limit minus 40 plus 0.01 times the fine particle percentage minus 15 multiplied with PI minus 10. This is the plasticity index. This is the percentage of fine particles. This is the liquid limit. And GI, that's the group index. This is the AASHTO classification of soil and soil aggregate mixtures. Okay, you have seen this before, right?
Yes.
Okay. Okay, guys, we are going to take just a break now, and we'll be back around 11.
Okay, that's okay.
Okay, we are back. We stopped here at the AASHTO soil classification, and we have here an example. Just to, you know, you have studied this before, but just to refresh our memories, we are gonna try. We have this example, and for the given sieve analysis and plasticity data for 3 types of soils, we need to come up with a classification for each one of these. So I moved this to the whiteboard, and we can see it here. So basically, let's start with soil number 1. Soil number 1, the first criteria that we look for is basically the percentage of soil passing sieve number 200. So here, passing number 200, okay, so we have, you know, passing number 200 is more than 35% passing. That means there's a lot of fine material here, okay, and in this segment, its passing sieve 200 is less than 35. So that's basically the cutoff of sieve number 200. So based on this, we can say that only soil number 2 is in category A. So this one is A1 or A2. But for this one, for soil 3, it's either A4 and goes all the way to A7. A4, and also for soil number 1 to A7. Okay. To write this in a better organized fashion, we can say soil 1 passing number 200 greater than 35. That means we have either A4 to A7. Then we go to the plasticity data. So based on the plasticity data, or the liquid limit and plastic limit for soil, okay, these are the conditions. the liquid limit equal 20. So that's the maximum 40 and the maximum 40. But here the minimum is 41 and the minimum is 41. So it's either A4 or A6. Then we go to the plasticity index. So the plasticity index here is 5. Pi equal 5. It's a 10 maximum and here 11 minimum. So it's A4. So this one is A4. Now for soil number 3. S3. What we got here? We got, it's, of course, we know it's either A4 to A7 because we have the percentage passing number 200 is greater than 35, right? It's 97. That's, greater than 35. So it's A4 to A7. Then we go to plasticity index or the liquid limit. Liquid limit equal 124. So here for the liquid limit, maximum 40, so it's not this one, and maximum 40, but it's either A5 or A7 -5 or -6. So it's this one or this one. So it's either A5 or A7, either classification. So we go here to the plasticity index. The plasticity index for this soil is 77. It say here 11 minimum and 11 minimum. It satisfies both. This one is not applicable. Here 10 maximum. So it's not satisfied. So it's in this area. So it's either it's A7. Now the question, is it A7-5 or A7-6? To answer this, it says here a plasticity index of A7-5 subgroup should be less than or equal liquid limit minus 3. So here that's the criteria. Let's check. Pi equals 77. Is it less than or equal liquid limit minus 30? So it's basically less than or equal. That's a check. 124 minus 30. Of course, it's not less than this. So it's not A7-5. So it's not it's A7. Therefore, it's A7-6. So this one A7-6. So for S2, for S2, the passing percentage from number 200 is less than 35%. So it's either A1 or A2 or A3. Now we need to check and see where is it going to fit. First of all, it says that the minimum passing number 40 here for the passing number 40. Passing number 40 equals 40. So it's not A3. Not A3, because A3 there is a minimum of 51. So now we eliminated this and we have either A1 or A2. Now let's go to check on A2. The liquid limit, no liquid limit, plasticity index, no plasticity index, no plasticity at all. So here, as we can see, the liquid limit for it's either A2-4, okay, or A2-6, based on the liquid limit. It's either A1B, and here actually it's also A1B or A2. So it's either, now it's either A2-4 or A2-6. Based on the plasticity index, it says that for A2-6, minimum 6, minimum 11, I'm sorry. So here it's A2-4, okay, or now A1-B. Now the question, okay, is it A1-B or A2-4? To resolve this issue, let's check sieve number 10. Sieve number 10, okay, I'm sorry, sieve number 40. Sieve number 40, here it's not retaining any on sieve number 40, so it's not A2, because basically it's 40%, and here, so this should be eliminated from the beginning. So basically it's A1-B. So this one is A1-B. Clear? Thank you, Yusuf. Okay, now we go back, and so that was the soil, the subgrade classification according to ASH2. Now we go to compaction. As you can see, this picture is from, I guess this is from World War II, and you can see, you know, it doesn't need explanation. Okay, that's because the runway is not well compacted, and that's the result. Okay, so how can we measure compaction? There are several test methods. We have what we call the core test. We have the sand replacement, which sand cone test referred, and there's the nuclear gauge. This is based on nuclear estimation for the compaction of the soil. And this is a plate bearing test, and the Boumage meter, that is with vibration and stuff, and the Boumage BTM pulse plus, that's also based on vibration or dynamic loading. So let's look at each of these methods. Most of these methods, for example, the load bearing, sometimes we use it, especially in case of piles, testing piles. We sometimes use the load bearing or the plate bearing. That's for compaction. So it's difficult to apply in constructing highways, because you cannot sample. We need to have a lot of samples along the segment of the highway under construction. So we cannot have this configuration for several points. Again, the sand core test, it's not the optimum, okay, because it depends on several factors. The dynamic loading, vibration, the pommage, both these are expensive equipment to get. So we are left with these two approaches, the nuclear gauge and the sand replacement. Again, this machine is expensive, and also it has some nuclear radiation, so this is kind of controlled and needs special technicians to deal with. But for the sand cone test, that's very easy to apply and very common and cheap, doesn't cost that much. However, this test can be cheated, unfortunately. So for you as a construction manager or someone in the site, you have to keep a good eye on the sampling and making sure that there is no foul play in this test. So the ASTM standard methods for the sand cone, it's basically we have a sand cone in this jar, and there is a metal cone, and we dig basically a hole in the soil. Then we take it out. So basically, this hole is hand excavated. We excavate a hole, maybe the diameter around 6 inches. The material, we save it in a container, okay, weighted and water content calculated. We keep it in the oven to dry it, then we calculate the water content. This hole, after excavating it from the compacted soil, we fill it with free-flowing sand, with a known density, okay, and the volume is determined then. In place with density is determined by the density with density of the soil can be determined by dividing the weight of the sample by the volume of the sand. By knowing the water content and the wet density, the in-place dry density is calculated. We can calculate the dry density afterwards. This is an explanation for it. And these are the different weights that we need to calculate in order to have this test done. Basically, we fill this jar with this white jar with the sand. This sand is calibrated, and we know the density of this sand, the free density and the uncompacted. And we have weight 1, where this filled like this. Then once we open the controller here, the sand drop, because it's filling the hole and filling the cone, by the way. So we take another measurements. That's W2. That's the remaining sand. Okay, so that's the sand, mass of sand cone before test, mass of sand cone after the test. The difference, okay, will be basically W3. W3 is basically equal W4 plus W5. The weight of sand here and the weight of sand in the hole. Okay, so W4, that's the mass of sand filling the cone, the metal cone, and the W5, that's the mass of sand filling the hole. Okay, so we know the volume of the cone, so we can subtract, okay, gamma sand multiply with V cone, so we get W4, and W3, we subtract W4 from it. So we end up with the weight W5. We divide W5, the weight of the sand that's in the hole, divided by gamma sand, we get the volume of the hole. Okay? Once we get that, we have the W6, that's the mass of soil extracted, the sample. Okay? We have the moisture content of the soil, which is basically the ratio of the wet and the dry, and the gamma will be the W 6, the weight of the sample divided by the volume of the hole. The dry sample is basically the gamma T over 1 plus W, which is basically the moisture content of the sample. Any questions so far? That's an example here. We have weight of sand cone before test. So this is the weight of the sand cone before the test. 6.83 kilograms. That's W1. Weight of the sand cone after the test. Once we filled the cone and the hole, we have this weight. So we have W2 equal 4.26. So this one 6.83. And the weight of extracted soil sample, the weight we get from here from the sample, W equal 1.42 kilograms. Then the density of sand, the calibrated density here, gamma sand equal 1.653 tons per meter cube. And the cone volume equal 0.667 liters. Now the trick is in units, so pay attention to this. He didn't mention for the weight of the soil, the wet soil or the dry. So we're gonna just assume it's dry soil or dry weight. So now we want to calculate the volume of the sample. Volume of sample equal the weight delta, or the weight of the difference in the weight, which is 6.83 minus 4.26 minus the weight of the sand in the cone. So here it's 0.667. That's liter. Liter, that means it's okay. Let's multiply it by 10 to the power minus 3. So now it's meter cube. Multiply gamma, okay, which is 1.653. This will be in tons. Multiply by 1,000 to in kilograms. So the volume, and this is divided by gamma sand, which is basically 1.653. So the volume of the sample equal, here it's going to be gamma of sand is 1.653, and here we have 5 point here 2 minus 0.667 multiply 1.653, because the 1000 will cancel out with 10 power minus 3. So here we will have 2.57 minus 0.667 multiply 1.653 divided by 1.653. So the volume 0.8874. What are the units here?
بس دكتور مو تحت بالطن؟
Yes, we created a big mess here.
مفروض نضرب تحت ب1000 كمان.
Hold a second. These are kilograms, okay, and these are now it's kilograms, but here this is ton, or we can say this is kilograms per liter, correct? So this is liter. Again, ton per meter cube equal kilogram per liter. If you multiply the upper with 1000 and divide by 1000, you get this. Check it. So the density equal the weight of the sample 1.42 divided by 0.887, and what we will get it's almost 1.6, but again, what's the units? Kilogram per liter, which is also 1.6 tons per meter cube. Okay, now let's just have a check whether we are working in the right direction or wrong or not. First of all, these volumes are going to be something in that neighborhood. You cannot get this in meter, for example, okay, because basically you are not going to fill 1 meter with almost 2.5 kilograms of sand. Okay, so once we are talking in kilograms, then the volumes here are going to be in the order of liters. Correct? Again, we have to pay attention to the values here. Okay, because the values, it makes a lot of sense. For example, if you come up with a density that is 16 ton per meter cube, is this a correct density? Huh? Does this value make sense for soil?
No.
Why? It doesn't make sense. You are correct. But why? Let me ask you a question. What is gamma for steel?
200,000, I think.
Gamma for steel, 7.85 ton per meter cube. Gamma for gold, that's one of the heaviest materials on earth. How much? Or the density, it has the highest density. It's almost 20 tons per meter cube. Can we have soil with this density? Heavier than steel? No. Okay? Because soil, it's made of, silica and sometimes, iron and some raw material, a different material. But it's not, the pure, steel is 7.85. So the soil can never be some value like this. Okay? Makes sense, ya shabab? What is the density of concrete?
25.
2.5 ton per meter cube. Okay? You are talking in SI units, 25 kilonewton.
Per meter cube.
Okay, per meter cube. That's fine. Okay, but in terms of mass, okay, it's in tons. It's 2.5 tons per meter cube. Okay, and again, the gamma steel, if in terms of kilonewton, okay, it's 78.5 kilonewtons per meter cube, and for gold is going to be 200 kilonewton per meter cube. So in this case, we cannot have gamma 160 kilonewton per meter cube. Can we have this? No. Clear يا شباب? Okay, this we're gonna conclude our lecture for today, and see you inshallah next week.
دكتور
Hold a second, please.